In this particular question, we have to check whether the product of the two complex numbers is real or imaginary. So let us begin by multiplying the numerator. So we have 2 plus 3i multiplied to 2 minus 3i. So we can use the identity 2 squared minus 3i whole squared. So we are using the identity that x plus a multiplied to x minus a is equals to x squared minus a squared. Similarly, we can do that for the denominator. So we have 3 squared minus a 4i squared. So we have 2 squared is equals to 4 minus 9i squared divided by 3 squared is 9 minus 16, 4 squared is 16 times I squared. Now we know that I squared is negative 1. So this becomes 4 plus 9 divided by 9 plus 16. So this gives us 9 plus 4 is 13 and 9 plus 16 is 25. So we see that the product of the two complex number is a real number. Now, anyways, without even solving, we could have said, we could have found out if the given product is real or imaginary. If we use the property that given a complex number z, which when multiplied to its complex conjugate always yields a real number. Now that's because the first complex number 2 plus 3i over 3 plus 4i is the complex conjugate of the other complex number. Meaning, if we find out the z bar, then that is simply 2 plus 3i divided by 3 plus 4i over bar. That gives us 2 plus 3i over bar divided by 3 plus 4i over bar. And the complex conjugate of 2 plus 3i is 2 minus 3i divided by the complex conjugate of 3 plus 4i, which is 3 minus 4i. So it is indeed that here we have the product of complex number to its conjugate, and it should definitely give us a real number. Let's move on to the next question. So in this question, we have two complex numbers added to each other. We have to check whether the given sum is real or imaginary. So let us begin by first finding the sum of the two fractions. So we have 3 plus 2i divided by 2 minus 3i plus 3 minus 2i divided by 2 plus 3i. So we take the LCM, which will be the product of the denominator. We have 2 minus 3i multiplied to 2 plus 3i. Then we are going to cross multiply the elements in the diagonal, which is 3 plus 2i multiplied to 2 plus 3i, and this product will be added to the product of the elements in the other diagonal. So that meaning we'll multiply 3 minus 2i and 2 minus 3i. So that gives us 6 plus 9i plus 4i plus 6i squared plus 6 minus 9i minus 4i plus 6i squared divided by, we have 2 squared minus 9i squared. I can see that the additive inverses, so 9i is going to cancel out negative 9i and plus 4i is going to cancel out negative 4i. So that leaves us with 6 plus 6 plus 6i squared, which is negative 6, and we have another 6i squared, which will be negative 6, divided by 4 plus 9i squared is negative 1. Now we see that all the terms in the numerator cancels out each other, and the final answer will be 0, and this will be a real number. So that means the sum of the two complex number is giving us a real number. Let us do another problem. So in this question, it is given that the complex number -3 plus I times e squared b is the complex conjugate of the complex number a squared plus b plus 4i. Now we have to find the values of a and b. So it's given that -3 plus I a squared b, if we take the conjugate of it, then this value is equals to a squared plus b plus 4i. Or the other way around, or we can say that -3 plus I a squared b is equals to the complex conjugate of a squared plus b plus 4i. So the conjugate of -3 plus I times a squared b will be -3, so I will be replaced by -I, so that gives us -I a squared b. So this value is equals to a squared plus b plus 4i. Now we are going to equate the real and the imaginary part. So that should give us a squared plus b, which is the real part of the complex number on the right hand side. That will be equals to -3. And we have -a squared b is equals to 4. So from here, we can find out the value of a squared, and the value of a squared will be equals to -4 over b. Now let us take this value of a squared and substitute into our first equation, a squared plus b equals to -3, and that should give us -4 over b plus b is equals to -3. Then we multiply throughout by b, so this will give us -4 plus b squared minus 3b. Now we rearrange it, so we get b squared plus 3b minus 4 equals to 0. Now this is a quadratic equation. Let's solve for the value of b. So we get b squared, so we are going to split the middle terms by using the constant coefficient 4. We have 4 times 1, the factors of 4 are 1 and 4. So we have 3, which can be written as 4b minus b. Minus of 4 is equals to 0. B, factoring out b, we have b plus 4 minus, so we can factor out -1 from the third and the fourth term, so that leaves us with b plus 4 equals to 0. Then we have b plus 4 as the common factor from the two terms, so we have b plus 4 times b minus 1. Then solving for b gives us b to be equals to either 1 or -4. Now that we have the value of b, let us substitute it back to our a squared value. So that gives us a squared is equals to -4 over 1, which gives us -4. So this is the value of e squared. So a will be plus or minus square root of -4, which gives us 2i. Will be plus or minus 2i. And the other one will be, for this one, a squared will be equals to -4 over -4. So we get a squared is equals to plus 1, which gives us a is equals to plus or minus 1. So these are the values. So when b is equals to 1 and b is equals to 1, then we have a equals to plus or minus 2i, and when b is equals to 4, we get a equals to plus or minus 1. Let's go to the next question. Before going to the next question, I would like to mention one fact, that here while solving for a, we were getting a squared is equals to -4. Now this equation is only going to be valid if a is imaginary or a is complex. I can say it's a purely imaginary number. So then only it is possible. Since in a question it's not mentioned whether a and b are whether real or imaginary, so we will accept this value. So we are going to, because complex number is a much more bigger set when compared to real numbers, so you can assume both imaginary as well as real value. So we are getting both real value a equals to plus minus 1 and an imaginary value which is plus or minus twice of I. So here you are given complex number x plus I times y is equals to a plus I divided by a minus I. And here it's mentioned that a is a real number. Now we have to prove that x squared plus y squared is equals to 1 and y over x is equals to twice of a divided by a squared minus 1. So let us begin by first finding the conjugate of the complex number x plus iy. So the conjugate of x plus iy will be equals to a plus I divided by a minus I whole over bar, and that should give us x minus iy is equals to a plus I over bar divided by a minus I over bar, which is equals to a minus I divided by a plus I. Now we're going to consider this one as equation number 1 and this one is equation number 2. Now we're going to multiply them, so that would give us x plus iy multiplied to x minus iy is equals to a plus I divided by a minus I multiplied to a minus I divided by a plus I. So on the left hand side we have x squared minus I squared times y squared, while on the right hand side we can see that a plus I gets factored out because they are common to both the numerator and the denominator, and so does a minus I, leaving us with 1. Now we have x squared minus I squared iy squared on the left hand side. That would simply give us x squared plus y squared is equals to 1, since I squared is negative 1. So this takes care of the first part of the proof. Now let us go to the second part. Now we start with the question again, that x plus iy is equals to a plus I over a minus I. Now what we're going to do, we are going to multiply the complex number on the right hand side by the complex conjugate of the denominator, which will be a plus I. So we do it to both the numerator and the denominator, and that should give us a plus I whole squared divided by a squared minus I squared. Now we expand the numerator by using the identity a plus b whole squared, and that should give us a squared plus 2a times I plus I squared divided by a squared plus 1. Now we write it in the standard form. So we have a squared plus I squared will become negative 1 and it will become a real number. So we have a squared minus 1. Now we're going to divide it by the denominator, which is a squared plus 1 plus I times 2a divided by a squared plus 1. Now this value is equals to x plus I times y. Now we equate the real part and the imaginary part, and that should give us the value of x equals to a squared minus 1 over a squared plus 1, and y will be equals to twice of a divided by a squared plus 1. Then we are going to take the value of y and divide it by x, and that should give us 2a over a squared minus 1. And this proves the second part. Let's go to the next question. So in this question we have that the cube root of a plus ib is equals to x plus iy, where a, b, x and y are all real numbers. Now we have to prove that a over x plus b over y is equals to 4 times x squared minus y squared. So let us begin by considering the given equation and we cube it both sides. So we have cube root of a plus ib equals to x plus iy. So we're going to cube it from both sides, and this will take care of the cube root. So the cube of a cube root will give us a plus ib Now we're going to expand x plus iy raised to the power of 3 by using the identity a plus b whole cube. That gives us a cube plus 3 times a squared b plus 3 times ab squared plus b cubed. So using this identity, we have x cubed plus 3 times x squared times iy plus 3 times x times iy squared plus I cube y cube. And that gives us a plus ib is equals to x cubed plus 3 x squared y times I. And we have 3x I squared y squared. So I squared is -1, so that should give us 3 times x y squared. And we know I cube is equals to -I, so that gives us -I y cube. So you're using the fact that I squared is equals to -1 and I cube is equals to -I. Now we take the complex number on the right hand side and combine all the real terms together. So we have x cubed minus 3xy squared. So this will be the real part. And then we combine the imaginary part. So we have 3x squared y minus y cubed. Now that we have a complex number in the standard form on both sides and they're equal, so we're going to equate the real part and the imaginary part, and that should give us a equals to x cubed minus 3xy squared, and b will be equals to 3x squared y minus y cubed. Now what we're going to do, we're going to divide the first equation, let's call it equation number 1, and this be equation number 2. So let us divide both sides of the equation by x, and that will give us a over x equals to, so x cubed over x is x squared, minus 3xy squared over x will give us 3y squared. And for equation number 2, we divide both sides by y, so that should give us 3x squared times y over y will give us 3x squared, and y cubed over y will give us y squared. Now that we have two new equations, let's add them up. So we have a over x added to b over x, and that gives us, so x squared plus 3x squared will give us 4 times x squared, and we have negative y squared added to negative y squared, negative 3y squared added to y squared, so that will give us negative 4y squared. We factor out 4, so that leaves us with 4 times x squared minus y squared, and this is the required proof. Let's go to the next question. So in this particular question, we are given the complex number a plus ib divided by c plus id is equals to x plus iy. So let this be equation number 1. Then we have to prove that a minus ib over c minus id equals to x minus iy, and a squared plus b squared over c squared plus d squared is equals to x squared plus y squared. So let us first take the conjugate on both sides. So that would be a plus ib divided by c plus id equals to x plus iy. So we take the conjugate on both sides, and that should give us a minus ib divided by c minus id equals to x minus iy, and let's call it equation number 2. Now what we're going to do, we're going to multiply equation 1 and 2, and that should give us a plus ib divided by c plus id is multiplied to a minus ib divided by c minus id, which will be equals to x plus iy multiplied to x minus I times y. Now a plus ib multiplied to its conjugate a minus ib will give us a squared minus I squared times b squared divided by c squared minus I squared d squared, which is equals to x squared minus I squared y squared. So replacing I squared by -1, we have a squared plus b squared divided by c squared plus d squared is equals to x squared plus y squared. So there we go. So we have proof for both the two parts. So when we take the conjugate of the given complex number, then we get a minus ib over c minus id equals to x minus iy. And we multiply equation 1 and 2, and that gives us the second part of the proof, which is a squared plus b squared over c squared plus d squared equals x squared plus y squared. Let's go to the next question. So we're given here that x plus I whole squared over divided by 2x minus I is equals to a plus ib. And using this information, we have to prove the given equation. So let us begin by writing down our equation. We have x plus I whole squared, so I'm rewriting it as x plus I times x plus I divided by 2x minus I, and this value is equals to a plus ib. So let's call it equation number 1. Then we are going to take the conjugate of equation number 1, which will be simply putting an over bar, and that gives us x minus I multiplied to x minus I divided by 2x plus I equals to a minus ib. So this becomes our equation number 2. Now we're going to take the product of 1 and 2, so that will give us, so let's find the product of 1 and 2. So that should give us x plus I times x plus I divided by 2x minus I is multiplied to x minus I times x minus I divided by 2x plus I, and this will be equals to a plus ib multiplied to a minus ib. So we're going to multiply x plus I to x minus I, and this particular x plus I to the remaining x minus I, and that should give us x squared minus I squared times x squared minus I squared divided by 2x squared, which will be 4 squared, minus I squared equals to a squared minus I squared b squared. Now x squared minus I squared will be simply x squared plus 1 times x squared plus 1 divided by 4x squared plus 1, which is equals to a squared plus b squared, and x squared plus 1 whole squared multiplied to itself. That gives us x squared plus 1 whole squared divided by 4x squared plus 1, which will be equals to a squared plus b squared. So here we have square root of a plus ib over c plus id is equals to x plus iy, and we have to show that the square root of a squared plus b squared over c squared plus d squared is equals to x squared plus I squared. So let us begin by taking the square on the both sides of the given equation. So that will give us a plus ib divided by c plus id is equals to x plus iy whole squared. So instead I'm writing it as x plus iy times x plus iy. So let this be equation number 1. Now we're going to take the conjugate. We're going to take the conjugate. So that will give us a minus ib divided by c minus id is equals to x minus iy times x minus I times y. So this will be equation number 2. Now we take the product of 1 and 2. So that should give us a plus ib divided by c plus id times a minus ib divided by c minus id, which is equals to x plus iy times x minus iy times x plus iy times x minus I times y. So that should give us a plus ib times a minus ib will be a squared minus I squared b squared divided by c squared minus I squared d squared, which will be equals to x squared minus I squared y squared multiplied to x squared minus I squared times y squared. So we replace I squared by -1. That gives us a squared plus b squared divided by c squared plus d squared equals to x squared plus y squared times x squared plus y squared. And we have a squared plus b squared divided by c squared plus d squared equals to x squared plus y squared whole squared. Now we take the square root on both sides, and that finally gives us square root of a squared plus b squared over c squared plus d squared equals to x squared plus y squared. So this proves the question and that's how it's done. So in order to solve this question, we begin with the right hand side. So this can be rewritten as y plus 1 plus I is multiplied to y plus 1 minus I, and we have y minus 1 plus I is multiplied to y minus 1 minus I. Now here we're going to use the identity that a squared minus b squared equals a minus b times a plus b. So we have y plus 1 whole squared minus I squared. This will be the combination of the first two terms multiplied to y minus 1 whole squared minus I squared. So that is the combination of the last two terms. And this should give us y squared plus 2y plus 1 minus of I squared will be plus 1, and y minus 1 whole squared, when we expand it, we get y squared minus 2y plus 1 plus 1. Let's combine it. That should give us y squared plus 2 plus 2y multiplied to y squared plus 2 minus of 2y. Now we're going to recombine this again using the identity a minus b times a plus b. So we have y squared plus 2 whole squared minus twice of y whole squared